And today is my pleasure to announce a talk of Naoufel Salhi devoted to self-intersection local types. Please, Naoufel.
Okay, thank you. So as Professor Andre just said, this is a talk about self-intersection local times as generalized functional. And this is based on joint work with Professor Andre. So my object of investigation is the following visitation measure that I will call mu2 of mu2. Which is associated to the increments of the Brownian motion. So WT is a d-dimensional Brownian motion. Delta 2 will always design the set of the simplex in dimension 2, the set of times S and T in 0, 1, such that S is smaller than T. So the measure, the visitation measure is defined as follows: mu2 of A is the indicator over delta 2, integral over delta 2 of the indicator of A of WT minus WS. This is for any Borel subset of RT. So this measure, it computes how much time ST, S and T, the increments of the Brownian motion spanned at the set in the set A. So if this visitation measure is almost surely absolutely continuous with respect to the Lebesgue measure in RT, then we denote its density by ρ2 of U. This index 2 just because we take one increment, so it's 2 times. Of course, we can generalize and take some number of increments, but in this work, we will just focus on one single increment of Brownian motion. Formally, the density can be denoted as follows. So ρ2 of at the point U from RD is the integral over delta 2, and here we have the Dirac delta function at the point U of WT minus WS. So formally, the value gives us how much time ST, the increments of the Brownian motion spent at the point U. Of course, it may happen that this measure mu2 does not have density, but still we can provide a meaning for this formal expression by considering approximation of delta U, Dirac delta U function. We know, for example, that if we consider this family of Gaussian density, P epsilon D, D is to denote the dimension here, Z in RG. We know that this family of function converges weakly to the delta 0 function. So if we consider P epsilon D of WT minus WS minus U, this will converge in some sense to delta U of WT minus WS. This limit is considered in any sense, in almost sure sense or any LP sense, and even as we will see later, we can even consider the limit in some Sobolev space with negative index. The two definitions are not different. We can check that if our measure, a visitation measure mu2 possesses a continuous density, then this limit will always exist and is equal to the value of ρ2 of U. Okay. In this work, we will not focus on condition of existence of density or the existence of such limit, but we rather will focus on the properties of these asymptotic properties of this density here, ρ2 of u, when u tends to the origin. Okay, first let me recall some, so this is our aim. First, let me recall some well-known facts about this subject. In 1983, Rosen proved that in planar case and the three-dimensional case, this visitation measure mu2 possesses square integrable density ρ2, which is continuous in the entire space, but not at the point 0. In greater dimension greater or equal than 4, this measure mu2 does not have a density. In dimension 2 and 3, also some mathematician managed to obtain some asymptotics around the origin of this density ρ2 of u. For example, Baradan in 69, also Le Gall in 85, they proved in the planar case that if we subtract from the density ρ2 of u the following expression, 1 over pi the logarithm of 1 over the norm of u, then we can find a limit in almost sure sense and in L2 sense also. In fact, this expression here is equivalent to the expectation of ρ2 of u when u goes to 0. And this is called the renormalization in the planar case. In the three-dimensional case, a little bit different renormalization was also obtained by Dior in 85, but it was not enough to subtract the equivalent value of the expectation of ρ2 of u. We also need to divide by some correction term here, this expression, in order to obtain a limit when u goes to 0 in L2 sense. In 95, a different description of the same object, ρ2 of u, in dimension 2 or 3, was obtained by Imkeller, Perez-Abreu, and Vives. Precisely, they obtained the Intervenor expansion of this density ρ2 of u. So the Intervenor expansion is the following sum from 0 to infinity. For each k, we have a sum over all the partition of the integer k, and we have these integrals over delta 2. We have here a product from 1 to d. Here, these are Hermite polynomials. I recall here the definition of Hermite polynomials. And we have here the increments of Wj. Wj is the component number j of the Brownian motion. And also here we have Hermite polynomials from uj divided by square root of t minus s. Uj is also the component number j of the vector u. And here we have our Gaussian density in d dimension from the point u. Okay. Let me recall briefly what is this Intervenor expansion. If we consider any random variable which is square integrable and measurable with respect to the sigma field generated by the Brownian motion, I will just denote it by sigma of w. The Intervenor expansion has the following form. This is the series k from 0 to infinity. Okay, this term here, ek of ak, this is a multiple e2 stochastic integral with respect to w1 and until wt, and ak is some deterministic function defined on 0,1 to power k, and which is a square integrable. The series converges in L2 sense, and for different integers k, the summands are orthogonal in L2. Of course, in our case here, these integrals appear because this Hermite polynomial here of this expression can be written in the form of multiple E2 stochastic integral with respect to Wj. And the order of integration is exactly Nj. Okay. Now our aim is to develop asymptotics from this Intervenor expansion. Precisely, we will try to obtain an almost sure estimate when u goes to 0 for the term of order k. So we will fix the k, and we will see how does this term of order k behave when u goes to 0 in an almost sure sense. This is quite different, of course, from the previous estimation. Okay, so to obtain such estimates, we will need some technical results. And we will begin with the following result. Here, we want to see how the integral over delta 2 of this Gaussian density of parameter t minus s and d of the vector u multiplied by 1 divided by t minus s to the power alpha. How does this integral behave when u goes to 0? As we see here, this integral here depends only on t minus s. So this integral with respect to s and t can be transformed in a one-dimensional integral, and we obtain the following equivalent expression when u goes to 0. Here, in the case when alpha is greater than 1 minus d over 2, we found some constant that depends on alpha and d. Gamma here is the gamma function. And in the denominator, we will find the norm of u to the power 2 alpha plus d minus 2, which is a positive power here. In the case alpha is equal to 1 minus d over 2, we find some constant again, but with the logarithm of 1 over the norm of u. Okay. The next technical result is the following. If we consider a one-dimensional Brownian motion W, then we have the following almost sure upper bound for these Hermite polynomials from Wt minus Ws divided by the square root of t minus s. Here we have some constant depending on n, divided by t minus s to the power n over 2, and exponent of the absolute value of the increment Wt minus Ws. We need, of course, such kind of estimates, because if we just go back to the Intervenor expansion, we see that we have such kind of expression that always appear here. For the proof of this almost sure inequality, the idea first is to consider the generating function of Hermite polynomials. Using this generative function, we can obtain the following series representation for this function from z for any complex variable z. So this exponent here is equal to the series from 0 to infinity, here this power of t minus s, and here Hermite polynomial, and divided by n factorial and z to the power n. Of course, this function here is clearly holomorphic with respect to z in the entire plane C. And so these terms here can be expressed in as derivatives of this function at the point z. Precisely, our t minus s to the power n over 2 and this Hermite polynomial from this expression is the nth derivative at the point 0 of this function. Now, because of course of the fact that it is holomorphic, we can obtain such a derivative at the point 0 using Cauchy formula. So we just need to integrate, for example, on the unit circle, the set of z with modulus equal to 1. This function here from z divided by z to the power n plus 1. Now, if we want to obtain an estimation for the absolute value, if we take the absolute value, of course, we can get the absolute value inside the integral, and this z to the power n plus 1 will disappear, and we just need to have an upper bound for this, for the modulus of this expression. We can check for that for complex numbers of modulus 1, this inequality here holds. And so we obtain our estimate. Okay. Next, we need this estimate for Hermite polynomials, which is a result that goes back to the works of Jego on orthogonal polynomials. If we take any alpha in the interval 1/4 and 1/2, we can find the constant C such that for any integer n and any real number x, we have this upper bound for hn of x exponent of minus alpha x squared. So here we have some upper bound involving this constant C and some expression depending on n and alpha. Okay. Now we can combine these three estimates to obtain the following almost sure upper bound for the term number k of the Intervenor expansion of √2 of u. Of course, each one from these Hermite polynomials with the wj inside, we have seen that it is less or equal than some constant, and we will have t minus s to the power nj/2 in the denominator, and let me choose, and we will have exponent of wj of t minus wj of s. Of course, wj of t minus wj of s can be just estimated. It is less or equal than 2 times the maximum of the Brownian motion in 0, 1. So these Hermite polynomials will be estimated. We will have some power of t minus s in the denominator, and we will have the appearance of these maximums here. We'll have exponent of 2z1 plus 2zd. And for these Hermite polynomial here, we use this the last inequality, this one, and we can get rid of this Hermite polynomial, but this Gaussian density will be transformed into pt minus sd of u divided by the square root of 2. And at the end, we use our first estimates of the integrals over delta 2 of Gaussian density with some negative power of t minus s. Okay. So the result at the end is the following. So absolute value of this term here is less or equal almost surely than some constant multiplied by the logarithm of 1 over the norm of u. This in the very first case, in the first term in the planar case. For the other terms in the planar case, and the other term, all the terms in three-dimensional case, we have this following upper bound with the norm of u to the power k plus d minus 2 in the denominator. And these constants c of 0 and c of k are deterministic. Of course, we can obtain explicit formula for such constant, but as we are considering each term, each fixed term for fixed k, we don't, for the moment, we don't look to estimate these constants. Okay, so these are the estimate that the almost sure estimate that we obtained in dimension 2 and 3. Okay, now for dimension greater or equal than 4, as we said before, our occupation measure mu2 does not have a density, but we can we can use approximation and find some limit of the following integral here. So in the same work of Inkeller, Pires-Abreu, and Vives, they prove that this limit exists, but in every Sobolev space d2 gamma for gamma smaller than 4 minus d over 2. Of course, here 4 minus d over 2 is less or equal than 0, so this is a negative index. And so our row 2 of u now is a generalized Wiener function. It is also described by it has an E to Wiener expansion, but this E to Wiener expansion does not converge in L2. More precisely, we need to multiply here each term of order k by k plus 1 with some negative index here, exactly gamma over 2, in order to obtain a series that converges in L2 sense. Let me recall briefly these, how are these Sobolev spaces defined. D2 alpha is in fact the completion of the following space. We consider all the random variables, which are square integrable and measurable with respect to the Brownian motion, but such that the E to Wiener expansion only contains a finite number of terms. In such a space, we can define the following norm with index 2 alpha as the sum from 0 to n, k plus 1 to the power alpha, and here the usual L2 norm to the power 2. If alpha is negative, the elements of D2 alpha are called generalized Wiener function. When this index is negative, these spaces are much bigger than the L2 space, which is in fact D equal to D2 0. For positive index, we find smaller spaces included in this L2 space, and the bigger the index is, the smaller the Sobolev space is. D2 plus or minus infinity are defined as D2 plus infinity is the intersection of these spaces here with positive alpha, and D2 minus infinity is their union, the union of the Sobolev spaces with a negative index here. Okay. So as our row 2 of u now is a generalized Wiener function, we will use some result to describe more precisely this row 2 of u. We will use this result from of Sujita, it was published in 87. If we consider the classical Wiener space W0D, which contains all the continuous functions from 0, 1 to Rd, which start from 0, endowed with its Borel sigma field and equipped with the standard Wiener measure. So this is a probability space where we can easily define the Brownian motion by simply considering the canonical process W T, we associate W of T. Excuse me, W, we associate W of T. And now if we have a generalized Wiener functional that belongs to D2 minus infinity, which is positive on the following sense, if the pairing with some F from D2 plus infinity, which is a positive, mu almost everywhere is always positive, then such a generalized Wiener functional is described by a unique finite positive measure in the Wiener space in the following sense. The pairing between phi and f is simply the integral with respect to this measure theta with index phi. Applying this theorem to our generalized functional that we call rho 2 of u. First, we observe that this rho 2 of u is positive because this is the limit of clearly positive random variables.
May I ask a question? So u is fixed now.
Yes.
Okay, so we study this limit for fixed u and find the corresponding theta u for fixed u.
For fixed u, yes, exactly.
Thank you.
Now rho 2 of u is a positive generalized Wiener function, and consequently we can associate to it a unique finite positive measure in the Wiener space, such that the pairing with this rho 2 of u will be described by the following integral. Now, the property that we will discuss for rho 2 of u are simply coming from the property of this measure theta u. First, we will describe the support of this measure theta u, always for a fixed u until now. So what we can say is that the support is included in the following closed subset of the Wiener space. I denote this set by EU. This is the set of all elements from the Wiener space, such that we can find an S smaller than T, such that Vt minus V of S is equal to U. To prove that the measure, the support of the measure is included in this set, we need to prove that if some phi does not belong to EU, then we can find a ball such that the measure of this ball is 0. Once we have proven this, then we can say that the support of theta u is included in this set u. Okay, now if we consider such a function f which does not belong to EU, then by continuity of such functions, we can find a positive R such that for any s less or equal than t between 0 and 1, the norm of phi of t minus phi of s minus u is greater or equal than R. Now, how to find the ball that will be of measure 0? It is enough to choose any R1 which is strictly smaller than R over 2. Okay, let us fix such R1 and take any R2 between R1 and R over 2. That will be just an auxiliary variable here. We can always find a good function f in D2 plus infinity that is located between these two indicators. Indicator of the ball of radius R1 and center phi, and the indicator of the ball of center phi and radius R2. In fact, we have even a much general result. If we take any subset, open subset from the Wiener space, and we take some neighborhood of this open set, then we can always find an element from D2 plus infinity which is greater than the indicator of the first open set and smaller than the indicator of the second open set. Okay. And now we will use this to in our computation. The measure of the small ball is of course equal to the integral of the indicator of this ball. And using this inequality, this is less or equal than the integral of f with respect to theta u. Now we can use the pairing because we have this from the definition of our theta u. And the pairing here is expressed as the limit of usual inner product in L2. So this is the limit when epsilon goes to 0 of the expectation of f of w and the integral of ρ2 of u. Of course, this is the limit of these random variables. So we consider also here these random variables. Now we use the second inequality. So f is less or equal than the indicator of this bigger ball. And this means that we are computing the expectation of the Wiener trajectories that belong to this ball, which means that the supremum of Wt minus phi of t is less or equal than, it is less than R2. And we also have this integral inside the expectation. Now, of course, here, in this Gaussian density here, we have in the exponent, we have minus the norm of Wt minus Ws minus u to the power 2 and the exponent. So to have an upper bound for that, we need a lower bound for this norm. To obtain a lower bound for this norm, we just need to go back to this here inequality, which is true for any S and T. We just need to introduce W of T and W of S, and we will get a good lower bound of this norm, and then an upper bound for minus this norm. At the end, we obtain that this expectation is less or equal than the following integral over the simplex. But here in the exponent, we will have r minus 2r2 squared divided by 2 epsilon. Now this expression does not depend on S and T anymore, and its integral easily go to 0 when epsilon goes to 0. So the measure of this ball is equal to 0. And we have the result. Okay. Next property that we will get for this measure is the following. Let me just go some steps and then I will go back. Next result is the following integral formula. We will prove that to integrate some element from d2 plus infinity with respect to this measure theta u, always for a fixed u, it is this integral is equal to the following integral: phi st of u p t minus sd of u ds dt, where phi st will be defined from the conditional expectation of eta with respect to wt minus w of s. Okay. To obtain this result, we will need some very small property, and this property, okay, we need some elements from Wellknown theory to obtain this property. Okay, so first we will define second quantization operator. If we consider the Hilbert space of all square integrable deterministic function from 0, 1 to Rd, and we consider a bounded linear operator A in H of norm less or equal than 1. If we take any random variable in L2, which is measurable with respect to the Wiener process, of course, it has such kind of e to Wiener expansion, as we described before. And these kernels AK, in fact, they can be identified Each AK can be identified with a unique symmetric multilinear Hilbert-Schmidt form AK defined on the product HK. Identified, I mean that there is an isometry, in fact, between such kind of n-linear symmetric Hilbert-Schmidt form defined on HK and the set of all kernels AK. And now that we have such multilinear Hilbert-Schmidt form AK, we can define a new one using this operator A in the following easy formula. AKA from F1 to Fk is AK from AF1 AFK. So we just put A in the variables of AK. So here we defined a new multilinear symmetric Hilbert-Schmidt form. It is well defined because this norm is less or equal than 1. And now that we have such new AKA, of course, it will be associated to one unique kernel that will denote AKA. Now, second quantization is defined as follows. Gamma A of eta is this following Intervenor expansion, but instead of taking AK, we will take AKA, these new kernels AKA. Okay. What I want to prove for this second quantization operator is the following property first. If we consider eta to be square integrable and measurable with respect to the Brownian motion, A with the same condition, bounded linear operator in H with norm less than 1, then we have these two properties. If the norm of A is equal to 1 and eta is in D to N, N here is simply an integer, positive integer. So if eta is in D to N, then the same for gamma A. If the norm of A is strictly smaller than 1, we have much more better result. If eta is just in L2, then gamma A of eta is in D2 plus infinity. Infinitely many times differentiable, and all the derivatives are square integrable. The proof is simple, using the Intervenor expansion of eta and the second quantization of eta. And we use this key formula, a key inequality here between these multiple stochastic integrals of this new kernel and these multiple stochastic integrals from the original kernel. The norm of A to the power 2k will appear. Now, if eta in D2n and the norm of A is equal to 1, if we compute this series, this will be less or equal than, of course, this is now 1. So this is less or equal than this series, which is finite because our eta is in D2n. So this is exactly the norm of eta in D2n, which is finite. And so this is, of course, the norm of gamma A of eta in D2n, so it is finite, and so we deduce that this one also belongs to D2n. In the case the norm of A is strictly smaller than 1, using also this same inequality, we see that for any integer n here, the series with the kernels from gamma A of eta is less or equal than k plus 1 to the power n norm of A to k and ek ak the L2 norm to the power 2. All we know in this case is that eta is square integrable, so the series of these terms converge. But since the norm of A is strictly smaller than 1, then this whole new series converge for any n in big N. And so we deduce that our gamma A of eta belongs to D2 plus infinity. Okay. Now I need this following proposition which shows that some link between second quantization and conditional expectation. Precisely, if we consider F to be a closed subspace of the Hilbert space L2 of 0, 1 to Rd, we can define a sigma field related to F in the following sense. We consider the sigma field generated by all these binary integrals of Hj of t with respect to Wj of t, j between 1 and d, and all this vector H1, Hd belongs to F. Well, let us consider also the operator of orthogonal projection onto F. Let us denote it by P. Now the relation is as follows. If eta is square integrable and measurable with respect to the Brownian motion, then this conditional expectation with this new sigma field is exactly the second quantization operator associated to the operator P applied to eta. So, okay. To prove this, first we observe that these two operators, gamma, the conditional expectation with respect to AF, and this operator gamma of B, these are two bounded linear operators of this L2 space here. And so it is enough to prove this equality for a dense family of such eta. And it happens that there is a specific kind of such random variables which are dense in this L2 space. These random variables is these stochastic exponent, which are expressed as follows. The product from 1 to d, exponent of the integral from 0, 1 to hj of t, twj of t, minus the L2 norm of hj squared divided by 2. H1, hd is an element h of the Hilbert space capital H. The linear span of such family of random variables is dense in L2, in this L2 space. So to prove the equality for such kind of random variables, okay, we will check it. The conditional expectation of exponent of h with respect to AF. First, we decompose h to be pH simply plus h minus pH. This belongs to F, and this is in the orthogonal complement of this belongs to F, and this is in the orthogonal complement of F. And we can check that in this case, the stochastic exponent will be the product of the two stochastic exponents. But now pH, of course, belongs to F. So the associated stochastic exponent will be measurable with respect to this sigma field. So we can get this variable outside from the expectation. And now this belongs, H minus pH belongs to the orthogonal operator. In such case, the stochastic exponent will be independent from AF. In fact, orthogonality here can be, by this expression can be mapped into independence. So this conditional expectation is simply the expectation. And we can check that for any h, the expectation of this random variable is equal to 1. So we find the stochastic exponent of pH. And finally, the last formula that we use is that the second quantization associated to the operator P applied to stochastic exponent of H is equal to stochastic exponent of pH. This is due to the fact that these random variables have some specific Intervenor expansion. And from that Intervenor expansion, we can deduce this formula here. So now we have our result for such specific family of random variables which span a dense subspace in L2, and we have the result for any element from this space. Okay, so now what we obtained is that this conditional expectation can be expressed as a second quantization operator. And we have seen that second quantization operator has some property of saving differentiability in this sense. So we can deduce that conditional expectation also have such kind of properties. So this is our theorem here. If eta is in D2n, always n is some integer here, then its conditional expectation with respect to AF also belong to the same space. And if eta is in D2 plus infinity, then of course means that it is in D2n for any n. So we deduce that we have this conditional expectation is in D2 plus infinity. This is an auxiliary result with its own interest, but of course we will use in the following result. So here, if we consider eta in D2 plus infinity to be bounded, then for each u in Rd non-zero, the integral of eta with respect to this measure theta u is expressed by the following formula, where phi st is defined as follows. Phi st of Wt minus Ws is the conditional expectation of eta with respect to Wt minus W of s. Moreover, both sides of this equality are continuous with respect to the variable u. Okay. For the proof, we start by considering this integral. And of course, this is the pairing between eta and our root of u, and we have how to compute this pairing. So root of u and eta, this is the limit of usual inner product, L2 inner product. So expectation of eta with and this integral here. And eta is bounded in such a way that we can put this expectation inside this integral here. And then we just need to make conditional expectation with respect to Wt minus Ws. So the expectation of eta multiplied by this expression here will be equal to the expectation of this same expression with phi st multiplied by phi st of Wt minus W of s. Now we have a new expression from Wt minus W of s. We use the density of Wt minus Ws, which is Pt minus Sd of x. And we just here the integral over Rd p epsilon d x minus u and phi st of x Pt minus s of d x dx. This is this expectation. This is a bounded expression, and these are integrable function, and we can reorder the integrals. Finally, we get the integral over Rd p epsilon d x minus u, and we have this integral over delta 2 phi st of x Pt minus sd of x ds dt then dx. Okay, if we look now to this integral here as a function from x, in order to have the value of this limit, it would be good if we have the continuity of this function from x at the point u. If it is continuous at the point u, then the limit when epsilon goes to 0 is the value of this function of this integral at the point u. So we will try to show that this integral here is continuous with respect to x for any x different from 0. Now the function inside the integral is should be bounded with independently from x, and it should be continuous with respect to x in order to apply the dominated convergence theorem and obtain the continuity of this integral with respect to x. Pt minus sd of x is continuous with respect to x, but this one phi sd of x, to obtain its continuity, we will come back to our last result. Okay, so phi sd is defined as follows. This is conditional expectation of eta with respect to wt minus ws. But as we have shown before, this conditional expectation, our eta here is in d2 plus infinity. So this conditional expectation will belong also to d2 plus infinity. And we deduce from that this function phi st is in d2 plus infinity, but in Rd, since wt minus ws is a d-dimensional vector. But d2 plus infinity in Rd, by Sobolev embedding theorem, this is included in continuous function from Rd. And so this function here, phi st, is continuous. Okay, now we can proceed. It is continuous with respect to this variable x. So this whole integrand here is continuous with respect to x for the an upper bound. To obtain an upper bound independent from x, as we are looking for continuity in Rd, but minus 0, so it is enough to check continuity in the set outside of a ball of radius r for any r positive. So we fix some positive r and we try to check continuity in this set. But of course, our eta, as we said in the here, it is bounded. So this function phi st of x will be bounded independently from x, from s and t. And pt minus sd of x, because of this inequality here, it will be less or equal than exponent of minus r to the power 2 divided by 2t minus s and divided by 2p times d minus s to the power d over 2. So we can also find an upper bound for this independent from x. And the whole new upper bound is integrable over delta. Finally, this integral is continuous with respect to x for each x in Rd minus 0. And the limit for this whole integral will be the value of this integral at the point u. Of course, the point u is non-zero. And we have our result. Okay. Next, a deduction from this last formula. If we come back here and just take eta to be equal to 1, of course, this integral will be theta u of the whole Wiener space. And here, this phi st is equal to 1, and we obtain the integral over delta 2 of this Gaussian density. And we have all, of course, we have estimates for such kind of integrals. So exactly, we will have some constant dependent on d divided by the norm of u to the power d minus 2 when u goes to 0. So here we look when u goes to 0, we have asymptotics of the measure of the whole space. Okay. Next result, or the final result, is that we will focus on the capacity of the support of the measure theta u. First, let me recall the definition of the capacity. If alpha is positive, if we consider an open subset of the Wiener space, the 2 alpha capacity is defined as the infimum of the norm of f into alpha squared, and f in d2 alpha greater or equal than the indicator of this open set O. For arbitrary subset of the Wiener space, the capacity is defined as the infimum of the capacity of the open sets that contain this set A. Okay. Our estimation will be based on the following result, again from Sujita. If we have a positive generalized Wiener function, which belongs to D2 minus alpha for some positive alpha, which is positive, and then of course it will be associated to some measure in the Wiener space that's denoted by nu phi. Then we have the following inequality for any Borel subset of the Wiener space. Nu phi of A is less or equal than the norm of phi in the 2 minus alpha Sobolev space. Here we have the square root of the capacity of this set A. And the same result, Sujita says that in particular, a measure corresponding to a positive generalized Wiener function never has X mass in slim sets. A slim set is simply any set that any capacity of such set is 0. Okay, in our case, we will apply this by taking our phi first is our rho 2 of u, our general, the associated measure is, we denoted it by theta u, and we will take as A to be the support of theta u. Okay, of course, nu phi of A will be theta u of the support. Theta u of the support is simply theta u of the whole space. And we have an estimation for the value of this measure of the whole space. And what remains is the norm in 2 minus alpha of our rho 2 of u. This measure here, this norm here is in fact estimated, well estimated in the paper of Peter M. Keller, Perez, and Weeks. So finally, we just need to put this estimation together and we obtain the following estimate for the capacity of the support. Always dimension greater or equal than 4, u is non-zero in RD, gamma is smaller than 4 minus d over 2. We can find the constant dependent on the dimension d and the gamma, this index gamma, such that the capacity, and this is 2 minus gamma of the support, is greater or equal than this constant times the norm of u to the power 4, and this when u goes to 0. Okay, this is our last estimates. Further topics may be to improve the obtained estimates, mainly to obtain the other side estimates. For example, it would be nice if we obtain an upper bound for this. And also, let me go back. We have here, where is it? Yes, and for this estimate, it would be nice if we can find some lower bound estimate. And second, it would be nice if we investigate the properties of joint properties, let's say, of this family of measures theta u. This is just still an idea. I mean, the distance between these measures, if we can do so, or the limit in some sense of this family of measures when u goes to 0 or any kind of such properties. These are some basic reference for this work. This is the first paper from Keller, Pérez-Abreu, and Vives, Gauss expansion of double intersection over time for in motion RV and renormalization. And this paper from Sujita describing positive generalized linear function and potential theory over abstract linear spaces. This is all what I have. Thank you for your attention.
Okay, thank you very much. Maybe somebody have questions or comments, please. Okay, let me just have a few comments. First of all, from result of Rosen, which you mentioned about the existence of the density, one can deduce not only the existence, but some regularity of the density in this case, of course, outside of 0, because he just used Fourier transform, and he proved that Fourier transform of the related visitation measure can be multiplied by some power of lambda, the argument of Fourier transform. Consequently, one can expect some regularity with respect to u of the our members of Intervenor expansion. So it can be interesting to check this regularity every issue. Of course, it can be different from the regularity in square mean. And then maybe we can deduce more precise estimations and estimate from other side our members of Intervenor expansion. Also, I think that it can be very interesting to check the regularity of the family of theta u in the same way. So we just can consider different distances between the measures and try to find the appropriate distance. Because of we already have something, some knowledge about the conditional expectation and so on, it seems that the distance related to some reproducing kernel based on the positively defined function can be useful here. So I think that here there are a lot of interesting questions, and I hope that Naoufel will show us next steps in this direction in new semester.
I hope so. Thank you.
Okay. Maybe some other questions. If there are no any questions, then I want to announce next session of our seminar, because it will be a specific session. As you remember, at the end of the spring semester, we have the special session of our seminar, which we call Scorehod Readings, where we unite together several talks of young mathematicians who are already students, magister students from different countries in theory of stochastic processes. Exactly such session will be next. And please pay attention to the announcement which you will have from our secretary, because it will start non-regular. It will start much more early, because we have 6 speakers, exactly as last year, and we will start in Ukrainian time like 2:30 p.m. So please pay attention to the announcement. Also, I must say that this semester was fruitful, despite of anything. and that I think we can start to collect the announcements, the types of the talk for the next semester. So thank you very much and see you next week. Bye.
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 Bye. See you next week. Bye.